channel. In this session, we'll discuss about one important concept of carbohydrate, that is fructose. We know that fructose is a very important monosaccharide unit of carbohydrate molecule, which is having the simplest molecular formulae C6H12 and O6. And we know that each and every monosaccharide unit is going to have the same molecular formula, that is C6H12 and O6. And we know that fructose, as the name itself telling you, it is a simple fruit sugar. And this fruit sugar, that means fructose, is present along with glucose in majorly in all these sweet fruits as well as in case of honey. So fructose is present along with glucose molecule. We know that fructose is one of the major constituent of many disaccharides as well as polysaccharide units. And fructose is having a melting point of around 102.7 degrees Celsius. This is the actual melting point of fructose molecule. And if you observe the detailed structure of fructose molecule, fructose is having ketone functional group. As well, we have already written a molecular formula. It is having 6 carbon atoms in its structure. Hence, we can call it as a ketohexose. So that is the general name that we can give for a fructose molecule. And we shall cover about the structural details of fructose molecule also. Firstly, we shall see about the open chain structure of fructose. Okay. So in case of open chain structure of fructose molecule, as we have already written, it is having 6 carbon atoms. So it will be having the structure like this. And there is some similarities between the structure of glucose and fructose molecule. So first position in glucose we will be having CH4, but here we are having CH2OH. And in second position we will be having CH and OH, but in fructose we will be having C double bond O, that is ketonic group. And all the remaining positions 2, 3 and 4. All the remaining 4 positions and the arrangement of H and OH in fructose will remain same as that of glucose. That is, at third position we will be having H and OH, and in fourth position also we are having OH and H, and at fifth position we will be having OH and H, and at sixth position it will be CH2OH. 1, 2, 3, 4, 5, 6. This is the complete open chain structure of fructose molecule. And you can observe the complete structure of fructose, and here among the 6 carbon atoms we are having only 3 asymmetric carbon atoms, that is the chiral carbon atoms. And we know that depending upon the number of chiral carbon atoms that are present in a given molecule, we can calculate the number of possible stereoisomers with the formula 2 power n. We know that n is the number of chiral carbon atoms present. And here we are having 3 chiral carbons. So 2 power 3, totally 8 stereoisomers are possible for fructose molecule. Okay. And you can notice here at the 5th position, this is the most asymmetric carbon atom, and at this position the OH group is present on the right hand side. Like in glucose, fructose is also having D configuration. And if you pass the plain polarized light through the solution of fructose, it has the capability to rotate the plain polarized light in anti-clockwise direction, that is towards the left hand side. Hence it is a levorotatory material, hence we can present with a negative sign. So the complete name of fructose can be written as D minus fructose. So this is the information we can clearly get from the open chain structure of fructose molecule. So as of now, we have given the open chain structure of fructose molecule, that's what we have written. But we know that, like in case of glucose, that what we are having anomeric form, that is alpha D glucose and beta D glucose. In case of fructose also, we will be having 2 anomeric forms, that is alpha D fructose and beta D fructose, which cannot be explained on the basis of open chain structure of fructose, which can be clearly explained only by cyclic structure of the molecule. So now we shall proceed to look over about the cyclic structure of fructose molecule. and cyclic structure will clearly explains the anomeric form as well. So few many phenomena such as mutarotation, which is already discussed in our previous video, and if you have not seen the video of mutarotation, the link is provided in the description. You can click over to the link to look over about the concept of mutarotation. And now we shall see about the cyclic structure of fructose-smalic here. And here we know that at the 6th position we are having a primary alcoholic group on which we are having lone pair of electrons, as well here also we are having ketonic group on which upon oxygen also we are having lone pair of electrons. And this primary alcoholic hydrogen is very active, and one of the lone pair of electron of the carbonyl group will be interacted with this hydrogen so that they develops a bond between oxygen and hydrogen. But due to manipulate the lone pair of electrons present on the oxygen, the pi bond will shift on to the oxygen, so that valency of the carbon will get disturbed, and for that purpose the lone pairs present on this alcoholic OH group will be donated to the carbon, and to balance this lone pair, the bond pair between oxygen and hydrogen will shift on to hydrogen. So there develops a link between the 2nd carbon and 6th carbon atom to develop a ring, that is the ethereal ring. And now we shall see how this interaction will develop the cyclic structure. First we shall write the alpha form, then the contrary of it, that is beta form will be written. And here CH2OH is the first position, and the second position, let's write OH group over here, and the third position CHOH, and the fourth position COH, fifth position COH, and at 6th position we are having CH2, which is linked with the 2nd carbon atom through the ethereal link. So this is the cyclic structure of fructose molecule. 1, 2, 3, 4, 5, 6. And here you can notice the first carbon atom of the ring is having OH group on the right hand side. So it is the alpha anomer having D configuration, and it is a levorotatory, and the material is fructose. That's the name of the first anomeric form. And we can write the second anomeric form also in the same train, but by altering the position of OH group at the first carbon atom of the ring, taking on the left hand side CH2OH, and all the remainings will be written as it is CHOH, COH, COH, and finally CH2 having a ethereal ring. And in this structure also you can notice 1, 2, 3, 4, 5, 6, right? So and at the first carbon atom of the ring, OH group is present on the left hand side. So it is the beta anomer having D configuration. Optically it is levorotatory, and the material is fructose. So here we have written the cyclic structure of the fructose molecule in both the anomeric form, that is in alpha form as well as in case of beta form. So for a carbohydrate molecule, along with writing the structure in the cyclic form, it is very convenient to present the structure of a molecule in Haworth form. So for glucose molecule, we know that the structure can be written in the form of Haworth form, that is a 6-member ring which is in analogy with pyron, right? So that's why we used to call it as Pyramus structure. And the fructose molecule is also having Pyramus structure, which can be placed by observing the arrangement of H and OH in this ring in the form of Haworth structure. And that we shall observe. First we shall go with the skeletal structure of Pyramus form, which is a 6-member ring like this. So 1, 2, 3, 4 and 5. Right? So this is the skeletal structure of Pyramus form. And if you know the cyclic structure, the placing of the groups at each terminal is very much easy. That we know that those components that are present on the left hand side should be placed on the top edges, and those groups that are present on the right hand side should be go to the bottom edge, right? So let us go with the first carbon atom of the ring. So wherein the left side we are having CH2OH, which will go to the top, CH2OH, and here it is OH. And so this is the first, second, third, fourth, fifth, and this is the sixth position. So at third position, OH is present on the top, H, and fourth position, H, OH, and at fifth position, H, OH, and you can notice at the sixth position we are having only two hydrogens over there. So this is the complete Haworth form of alpha D fructose, but the name will change like alpha D minus, and it is the Pyramus structure, so we should call it as fructopyranose. That is the Haworth form and its corresponding name. Let us write the Haworth form for beta D fructose, and let us have the skeletal structure first. So this is the structure. So we know that it's a 2, 3, 4, 5, and 6. Everything will be same for both alpha D fructopyranose and beta D fructopyranose, except the arrangement at second position, that is OH and CH2OH. So this two groups will get flipped. So OH will go to the top and CH2OH will come to the down, and all the remaining arrangement will be as it is. And here it is OH, H, H, OH, H, OH, and here it is H and H. That's the Haworth form of beta D fructose. And let us write the name alpha D minus it's the beta form. So beta D fructopyranose. So this is the Haworth forms of glucose molecule. But listen to me, if you observe the structure of fructose molecule, which is going to obtain when you hydrolyze a sucrose molecule, we know that sucrose is a combination of 1 unit of alpha D glucose and 1 unit of fructose. And if you observe the structure of fructose in sucrose molecule, it will be not having this pyranose form, and fructose will be existing in a 5-member ring, that is, it will exist in the form of furanose. And let us see how the furanose form of fructose will be. And as I said, in case of sucrose, the fructose will exist in a 5-member ring structure, which will be having a skeletal structure in this way, like this. So at the first position, we will be having CH2OH, and this is the OH, OH, H, H, OH, and here it will be H, CH2OH. So this is the thing. And you can observe at the first position of the ring, 1, 2, 3, 4, 5, and 6. At the first position of the ring, the OH group is present on the bottom edge, so it is alpha D minus fructo, but not going to return as pyranose. Since it is a 5-member ring, it should be called as furanose. So that's the name of fructose molecule. So as we have written the alpha D fructose structure, we can write the beta D fructose structure just by flipping the groups that are present over here. CH2OH if comes down, and OH group if goes up, then the structure will be beta D fructofuranose. So fructose can exist in both 6-member ring as well as in 5-member ring structure. And that's somewhat a discussion between fructose about its open chain structure, closed chain structure, and its Haworth forms. And now we shall proceed further the way of conversion of the two monosaccharide units, that is glucose and fructose. So both can be easily interconverted. Actually the thing will happen in our biological system for necessary changes that are supposed to happen in a biological system. So glucose will convert into fructose and fructose will convert into glucose. And now we shall see the detailed reaction pathway for the conversion of glucose into fructose and fructose into glucose. And now we shall see the conversion of glucose into fructose. So here we have written the structure of D-glucose, and let us proceed the reaction pathway by which we can convert glucose into fructose. So firstly, in order to convert glucose into fructose, the glucose molecule is supposed to react with phenyl hydrazine. pH, NH, NH2. This is the simplified structure of phenyl hydrazine, and this doubly bonded oxygen will combine with the two hydrogens, and that results in the elimination of one molecule of water, and that results in the formation of C double bond. H will remain as it is, and here it is N, NH, pH, and here C, OH, H, C, H, OH, COH, H, COH, H, and CH2OH. This is the product we are going to get, and this is called, which is produced is glucose phenyl hydrazone. Since we are reacting with hydrazine, the resulting material will be glucose phenyl hydrazone. And this glucose phenyl hydrazone is once again reacted with phenyl hydrazine, NH2, NH, pH. The lone pair of electrons present on the nitrogen will be donated to this hydrogen. So that results in the elimination of NH3, and these two electrons will shift between carbon and oxygen, creating carbon-oxygen double bond, and this hydrogen will be attaching to this nitrogen, and that eliminates PHNH2. That is, one molecule of ammonia and one molecule of aniline will comes out, and here between carbon and oxygen these bond pair of electrons will get shift, and that develops a carbon-oxygen pi bond. That means we are getting a ketonic group. So CH double bond N, NH, pH, C double bond O, C, H, OH, and at fourth position, fifth position, and at sixth position we'll be having CH2OH. Right. So once again, the molecule will interact with NH2, NH, pH, because we are having doubly bonded oxygen once again. So this oxygen will get combined with the hydrogen, and that results in the elimination of H2O. So we are going to get CH double bond N, NH, pH, and once again C double bond N, NH, pH, and third position, fourth position, fifth position, and at sixth position CH2OH. Right. So here we got glucosazone, and this glucosazone is further subjected for hydrolysis with the dilute HCl. So when you perform hydrolysis of this glucosazone with dilute HCl, this phenyl hydrazone, this group that is connected with carbon through double bond, will get eliminated in the form of pH, NH, NH2. That is, phenyl hydrazine will come out and creating once again oxygen, because dilute HCl in the sense will be having water molecule. So oxygen will come over here, and that gives rise to C double bond O. And here also the group which is present, pH, NH, NaN, will get eliminated in the form of pH, NH, NH2, and here also we are getting oxygen. Okay, so we will be having C double bond OH, C double bond O, C, H, OH, and at fourth position, fifth position, and at sixth position we will be having CH2OH. So just notice the names of the materials. It is glucose zone, and here we are going to get glucose zone. Okay, and almost we comes to the end, and here you observe, in case of glucose we are having aldehyde, am I right? And here we converted one of the OH group into ketonic group, but in order to protect the first position we have remained with the hydrazone format, and here both have been recreated, aldehyde and ketone, and now we have to retain this ketone and we need to get oxidize this aldehyde, we need to reduce this aldehydic group to the form of alcohol, because we know that in case of fructose the first position will be CH2OH, so aldehyde is supposed to be reduced to get alcohol. And for the purpose of reduction, the reduction will be performed in presence of zinc in acetic acid, or you can use hydrogen in nickel. So the aldehyde group will get reduces into the form of alcohol, so it will get changes into CH2OH, C double bond O, C H OH, and at fourth position, fifth position, and at sixth position we'll be having CH2OH, and that's the material what we required. It is D-fructose, and this is the way how we can easily convert one molecule of D-glucose into a molecule of D-fructose. This is the detailed pathway for the conversion of glucose into fructose. And now we shall go further with the converse. That means conversion of fructose into glucose. Now let us look over about the conversion. Let us see the way of conversion of fructose into glucose. And in order to convert a fructose molecule into glucose, first we need to change this carbonyl group which is having at the position number 2 to H and OH. That means we need to reduce the system. So for the reduction purpose, we shall have a reducing agent, sodium amalgam, so that reduction can be done. So here CH2OH will remain as it is, and now C double bond O will be changed to CH and OH, and all the remaining position will be undisturbed. Fourth position OHH, fifth position OHH, and at sixth position we will be having CH2OH. Here one possibility is there. So if OH is to the left hand side and H is on the right hand side, it will be mannitol, and for this structure it will be sorbitol. That means when fructose is subjected for the reduction, there is possibility of formation of both sorbitol and mannitol. So this will be mixture of both sorbitol and mannitol. But in order to get glucose, we need only sorbitol. If you proceed with mannitol, you are going to get mannose. And if you proceed with the same mixture, some percentage of glucose and some percentage of mannose will be obtained. But since we are focusing only on conversion of fructose into glucose, we are in requirement of only sorbitol. So from this mixture, we need to separate the mannitol. So when you separate the mannitol, we are going to get only sorbitol. So OH, H, and at third position H, OH, fourth position OH, H, fifth position OH, H, and at sixth position we will be having CH2OH, and this is our sorbitol. And this sorbitol is further subjected to this sorbitol is further subjected to the process of oxidation, and the oxidation will be done in presence of strong oxidizing agent like nitric acid, concentrated nitric acid. In presence of concentrated nitric acid, the first position, which is a primary alcoholic group, will directly get oxidized to the form of carboxylic acid. So we are going to get COOH group over here, or else let me write in this way: C double bond OOH, C OH, H, and at third position, fourth position, fifth position, and at sixth position we'll be having CH2OH. So this is D-gluconolactone. Okay?
Yeah.
So when primary alcoholic group is oxidized to carboxylic acid, we are going to get D-gluconic acid. And this D-gluconic acid is further heated to mild extent wherein this OH group and OH group present at the fifth position will get interact. So when D-gluconic acid is heated, the carboxylic acid and the OH group which is present at the fourth position will get interact so as to eliminate one molecule of H2O. That means this complete OH and this OH will completely interact so as to eliminate water. So we are going to have C double bond O, C, OH, H, C, H, OH, and at fourth position, OH, H, and at fifth position, OH, H, and at fifth position we'll be having CH2, OH, but as I said, the fourth position OH has been interacted with the carboxylic group at first position, so we'll get a cyclic structure. This is called gamma D-gluconolactone. That's the name of this intermediate. And at last, when this D-gluconolactone is further subjected to the process of reduction in presence of sodium amalgam, this OH will get one hydrogen and this carboxyl group will get this carbonyl group will get one hydrogen. So we'll get CH double bond O, C, OH, H, C, H, OH, and at fourth position CH, and this ethereal oxygen will receive one hydrogen from the reduction process, so OH will get regenerated, and at fifth position OH, H, and at sixth position we will be having CH2, OH. So collectively we got 1, 2, 3, 4, 5, 6 carbon atoms in straight chain, and this is the material D-glucose. And that's the simplest way of converting D-fructose into D-glucose. So these are the two important reaction pathways for any BSc level examination. As well, the interconversion of these components will be asked in any of the competitive examinations like IIT JAM, CSIR NET, or in any state level eligibility test or in GATE examination. In majority of the competitive track, the interconversions will be asked. Like what happens with the material it is going to produce when sorbitol is subjected to the process of oxidation in presence of concentrated nitric acid. The answer must be D-gluconic acid. So that should be present in one of the options. So like this the questions will be framed in competitive track. Okay, and that's all about the session, and in the next session we shall look over about the few many other concepts. Thank you.